Hi, this is Tim from the Ford Astronomy Club. I thought I'd give you a little bit of a presentation on the transit of Mercury, explain what a transit is and why transits happen. The reason for my timing of doing this particular presentation now is because we're about to have a transit of Mercury. As I'm recording this, it'll happen in about a month. The date is May the 9th, 2016. If you are in North America, it will happen very early in the day at sunrise for people on the east. If you're on the west coast, the transit will already be underway before the sun comes up, but you'll get to see the last part of it. You just won't see the very beginning. And so this is a simulation software. I'll talk about the software in a minute. Set up for that particular day on the morning, and you can see the sun is sort of hiding behind these trees. And let me zoom in a bit for you and put the day in motion so we can watch this happen. Now I'm really speeding up the timeline here. So the sun is coming up much, much faster than it would. And you can see the indicator for Mercury. I'll zoom in a little bit more. And you can see there's this little black dot. And it appears to be going across the face of the sun as the day progresses. And so here I am around 7:30 in the morning. And this will keep going on into the early part of the afternoon before it eventually passes off the other side of the sun and the transit event is over. Okay, so that's what a transit is if a planet appears to pass directly in front of the sun, so it is obscuring part of the sun's disk, a little tiny bit of it because Mercury isn't very big, we call it a transit. It's not called a transit if it appears to miss the sun completely. And the reason that these happen is because, in this case, Mercury is closer to the sun than the Earth. So as the Earth is going around the sun, Mercury is going around the sun faster than the Earth. And as Mercury passes on that sort of inside lap, if you will, if you want to think of it as a racetrack, as it passes on that inside, if it happens to pass directly in front of the sun, then we have a transit event. And so perhaps now you might be thinking, well, what do you mean if it happens to pass? Wouldn't that happen every single year? In fact, wouldn't it happen more often than once a year? So let me just talk about that. So I'm going to change the view a little bit here. And whoops. Okay. And now I've got a different image for you being animated. I'll zoom in a little bit. And I've got an animation of the inner solar system here. And let me just center it on the sun. That'll make it a little bit easier. Change my location scroller so I can move around, get the Milky Way out from behind us, and back out a little. And so you can see the everything going around. You can see the asteroids going around in the background and the planets going around. But let me give you a slightly different view of this. And so you can see clearly here's Mercury and Venus on the inside tracks. Earth and then Mars, of course, is on the outside track. This is only showing us what we call the inner solar system. So let me give you a different view. And here is a different view. This is a top-down view of this part of the solar system. I've centered on the sun, and it's currently not in motion. That's okay. I don't need to put it in motion just yet. But let me do this. I'm going to tilt the solar system on its side and watch what happens. You see the plane, these rings going around the sun that represent the orbits of each of these planets. Notice they don't line up. They're not actually flat to each other. So the green ring is the orbital path of the Earth. By the way, as we live on the Earth, to us, it seems like what's happening is the Earth is standing still. I did say it seems like it. It's not standing still, but it seems like it stands still. And it seems like day to day, the sun appears to be moving through the background sky. And in fact, if I turn on the constellations, let me see if I can just do that, turn on the stick figures and the labels, and there they all are. And that means that the sun appears to be taking a path across the sky, and we have a name for that path, and that path is called the ecliptic. And so it's the path that the sun appears to take going across the sky. And it passes through these constellations. By the way, notice the names of these constellations. So over here we have, I'll move my mouse. We have Libra here. We have Virgo here. We have Scorpius here, right? We have Sagittarius here. If these names seem familiar to you as the signs of the zodiac, that's because the ecliptic path passes through these 13 constellations. I know if you're into astrology, you think it's 12. It is in fact 13. So astrology gets it wrong, but passes through 13 different constellations, right? And but it doesn't really pass through those. What's really happening is the Earth is going around the sun, and so we call that line the ecliptic plane. We selfishly declare that we Earthlings living on Earth, that the plane that we orbit in is the plane that's flat, and that defines the ecliptic. And every other planet is inclined relative to the ecliptic. And so far, the people who live on the other planets have not shown up to protest our assertion of that statement of fact, that we're the ones that live in the flat plane and everybody else is tilted, right? So I'm doing this a little bit in jest, right? Because clearly we're a little bit off. And in fact, if you use the sun's equator, I think we're actually inclined quite a bit by about, I think, 7 degrees. So in any case, so there we have it. Let me turn off these constellations to make it easy to see. I'll turn off those. I also want to turn off the planets that we're not interested in. So I'm going to turn off Venus, and I'll turn off its orbit. And I'm going to turn off Mars, and I'm going to turn off its orbit. Okay, and now we're left with and I'll turn off the moon. We don't care about the moon. And now you can see just the orbit of Earth and Mercury. And you can see that they're very, very tilted against each other. And let me just I'm going to orient this over here. I need to change the date a little bit. By the way, so there is this point where these two planes intersect. And I'll zoom in a little for you. And so you can see here's one of the intersection points. And by the way, on the other side of the sun, there is another one. So I can have, oops, there it goes, right about there. There's the other intersection point, right? Because our orbit is obviously very consistent year after year, it turns out we will only appear to see Mercury pass in front of the sun if we are at one of these intersection points. And so you're thinking, well, why is that, right? So, when I look in a book, Earth and Mercury are kind of big and the sun isn't that big. So it seems like Mercury should pass in front of the sun all the time. Well, let me give you a scale model. If you have a basketball, right, the Earth is the size of the head of a pin, just a little less than 1/10 of 1 inch across. So if it were exactly, a basketball has a diameter of just about 10 inches. It's not exact, but work with me here. I'm going to round it off and call it a 10-inch sphere. And the Earth is just a little bit smaller than 1/10 of 1 inch. If the sun were 10 inches, it's actually 1/109th instead of 1/100th. But if you had a 1/10 of an inch, that'd be pretty close. Mercury is quite a bit smaller. By the way, our little head of our pin needs to be 90 feet away, again I'm rounding, from that basketball. So basketball, head of a pin, 90 feet apart. Mercury would be 35 feet, roughly, again I'm rounding, from that basketball. And a substantially tinier pin, if you want to think of it as a head of a pin. And so it turns out this red line representing the orbit of Mercury here, and the green line that represents the orbit of the Earth, that tilt, that angle there, that's a 7-degree angle. And so it turns out we have to be pretty close, both planets have to be pretty close to this little intersection point. If they're not very, very close to that intersection point and at the same time, then you don't have a transit. You miss it that year, right? You get about 30 13, maybe 14 of these transits in a 100-year period. By the way, one other thing about this is that this intersection point on the near side here, that intersection point is November. Earth is there in November. And if I zip it around to the other side, the intersection point on this side, right about there, okay, that intersection point, that's May. And for some strange reason, transits happen more often for Mercury in November than they do in May, about 2 to 1. I'm not quite sure why it worked out that way, but it does. So we're only going to see a transit if the Earth happens to be at this point in May. And well, the Earth will be in that point. The Earth will be here in May every single year, right? The question is will Mercury be at that point in May? Because Mercury goes around the sun in about 88 days, and Earth, of course, 365 days, 365 and a quarter, again, rounding. So let me just set my date here. May the 9th. Oops, let me back it up to the 9th. Not quite there. Oh, and I got to fix the year. The year's way off. There we go. Okay, so now I have set the date to May the 8th, 2016. I'll set this to the 9th. And let me set it to, well, it's fairly early in the morning. Okay, so we're on the wrong side of the sun. So we have to get to this side of the sun. And then you can see there's the Earth and Mercury both in the foreground. I'm going to try and line these up. I don't know how well I did. I'll zoom in. We'll find out how well I did. Okay, I'm a little bit off. Let me see if I can fix this a little bit. That's pretty close. Okay, now I'm going to set this at a 1 minute interval, which means every second of real time, a minute goes by. And let's just put this in motion here. And there you go. You can see the Earth, the Mercury, and by the way, the other little dot is our moon. What we see on Earth is just the dot for Mercury. Obviously, we're not going to see, this is like if I were in a spaceship way out in the solar system, maybe back perhaps by the orbit of Mars, that far away, looking backward, this is what I'd see. The sizes of these black dots are all horrendously exaggerated. The dots are actually much smaller in reality. So again, this is simulation software. So it's the timings are close, but and the positions are very accurate, but the sizings have been exaggerated because otherwise you wouldn't be able to see these things. So that's what you get at a transit of Mercury. Now, one more thing about the transit of Mercury. So May the 9th comes up, and you're very excited, and you would like to see this transit of Mercury. There is a problem. You must not look directly into the sun with unprotected eyes. You'll go blind, right? And you've heard this, and I ask students when I do presentations to students, how many of you have been told not to do this? And of course, they all raise their hand. And then I ask them, how many of you did it in spite of the fact that you were told not to do it? And of course, they all raise their hand. The catch is you don't go blind when you glance at the sun for a second. You have to look at the sun for several seconds. And the amount of seconds that you can get away with varies by the person, your age, how tiny your pupils will dilate, and all sorts of other factors. But it's not very long. It's substantially less than a minute. It's dangerous. So I don't want to tell you, you can look at the sun for X number of seconds because you'll sit there with a watch and then half of you will go blind anyway because these timings are based on averages. And so, half of the people are, longer than the average and half the people are shorter than the average. And so if I give you a number like that, half of you are going to go blind. And I don't want anybody to go blind. So how do you do this without actually going blind? By the way, if you cheat, right, you'll think you got away with it. It turns out the blindness doesn't set in right away. It takes the eye a day, maybe 2, before the effects really hit hard. And so you think you got away with something, and then 1 to 2 days later, suddenly you realize you have a very serious vision problem, and you need to go to the eye doctor, and it may not be reversible, right? So dumb idea, don't look directly into the sun. So how do you see this thing? Well, you use something called a solar filter. I buy my solar filters from a company called Thousand Oaks Optical. You can find them on the internet. There are other companies. I think AstroZap sells solar filters. Kendrick sells solar filters. So different companies sell solar filters. If you find actual telescope dealers on the internet, there are a handful of them. Most of them seem to be on the West Coast, but there are a few across the country. Legitimate telescope dealers tend to actually carry these things and sell these things. You won't find them at normal stores. Don't go to Best Buy or something looking for a solar filter. They're not going to have that. What's the solar filter? It's a very dense piece of optical film or optical glass. It filters out 99.999% of all the sun's light. Now that's 5 nines that I just rattled off. That means that one photon out of every 100,000 can make it through the filter. And so it's really blocking almost all of the sun's light. And yet you still see this, round dot of the sun, very obvious. It's just not overwhelmingly bright anymore, but it is very obvious. And then you'll see the black silhouette of Mercury going across the sun. You can put these filters in front of binoculars. You can put them in front of telescopes. It looks like a cap that goes on the front of the scope. But you only want to use a filter, again, that's designed specifically as a solar filter for looking at the sun. I've heard of people using welding goggles, right? I do not advise the welding goggles. It turns out there is one particular grade of welding goggles that is safe. Most, however, the vast majority of them are not safe. And looking through and deciding that it looks rather dim is not an indicator of safety. Let me tell you why. The sun puts out almost as much energy in the infrared spectrum, which our eyes cannot see at all, as it does in the visible spectrum, which our eyes can see. And many of these welding goggles, in fact, most of them, are really only designed to block the light that welding torches are giving off, which is not the right part of the spectrum to block for the sun. And they typically don't block any infrared energy. And you can go blind from this infrared energy, which your eyes can't even see, but yet it's still damaging the back of your eyes. So don't do that, right? So if you want to look at the transit of Mercury on May the 9th, you need proper solar filter, or you need an indirect viewing method. You can look up, which means you're not looking at the sun at all. You're looking at a shadow on the ground or a shadow on a piece of paper. You can look up how to do indirect viewing. There are many people that will show you how to make concoctions out of aluminum foil and a piece of paper. In any case, that transit, May the 9th, 2016, very early in the morning, right at sunrise is when it begins. If you're on the East Coast, if you're on the West Coast, obviously this transit has been underway for a few hours before the sun rises. It ends for those on the East Coast in the early part of the afternoon. So that's it. Transit of Mercury, why we have transits, why we're going to have one this year. But in most years, we don't actually have them, and what a transit is. I hope you found that helpful. Oh, last point, the software that I'm using to simulate all of this is Starry Night. I stumbled onto Starry Night a few years ago. It's very user-friendly. I know a lot of people talk about Stellarium. Stellarium doesn't let you leave the planet, and its functionality is relatively limited. It is free. People like Stellarium because it's free, but there's a lot of really cool things that you can do with Starry Night. So I've become a really, really heavy user of this software. Anyway, that's it. Transit of Mercury. Again, this is Tim from Ford Astronomy Club.